Hi audience and student. Today we start talking about the sampling effect of color mode control and its S-domain model. This is very important and interesting topic. So first we'll discuss the origin of the sampling effect, where the sampling effect is coming from. We didn't mention the sampling effect when we are talking about the voltage mode control, but why we suddenly start worrying about sampling effect for the color mode control will be explained first. Then I'll briefly explain the modeling approach to the sampling effect, how to model the sampling effect and how to incorporate the effect of the sampling to the small signal model of the converter. Okay. And there is one guy, Ridley. He proposed the new model which describes the S-domain characteristic of sampling effect, and we will review this. Okay. And this is my personal and final comment. And in the past, sampling effect was considered something really important and something really difficult. But now I found the sampling effect is just adds on to the classical modeling and design. This means we'll retain the main frame of the classical modeling approach and the analysis method and the design approach, and we add something extra. On the top of that, there is the sampling effect. Okay, add-on is something you add to decorate something or to improve something. Okay, in the past, the sampling effect was considered really important, but now I understand this is the simply add-on. Something is not absolutely necessary, but something is not bad or not good to know. Okay, but understanding this at least once is critical to understand this color mode control and the sampling effect, and to be comfortable with this color mode control. Okay. Maybe Ridley got upset by seeing this or listening my lecture, but that is true. Okay. Later on you will understand this. All right. So we review the P color mode control, and the purpose of this slide is I want to explain to you why the sampling effect is only pronounced in the color mode control, not in the voltage mode control. Okay. First, consider the voltage mode control. This is the PWM waveform of voltage mode control. In voltage mode control, we have this fixed ramp signal, and we are comparing with this control voltage V con. This is V con. Control voltage. For ideal case, this control voltage constant. So you have this horizontal line here and the switching action across here. Okay. Even though it's the piecewise linear function, everything is fixed. So this is the fixed, and this is control voltage is fixed for the ideal case. But in real situation, there will be some sinusoidal oscillation, very relatively small oscillation compared to this DC component. So in practical case or real case, this control voltage will be different from the ideal case, and it has some sinusoidal oscillation like this. But this point is where the switching action is done. So at this point, where the switching action is performed, remain the same. Okay, so that is the definition of steady state. So duty ratio is fixed. That means this point is fixed. Then effectively, you can replace this sinusoidal wave with this straight line, linear line segment. They are same. Okay, they are different, but in terms of their functionality, they are the same. Okay, so everything is fixed. So even though there is a sampling action here, the sampling effect is not pronounced. Okay, but situation is different. This is the control waveform of P color mode control. Again, we have fixed V lamp signal, and we have this control voltage here. Okay, assume this is constant. Then this is the VI. Okay, VI is derived from the inductor current. So inductor current is another constant. It's increasing. This time period, decreasing, increasing, and decreasing. So, and they are added together. So actually this fast varying inductor current is reflected to composite control signal. So this is the VI plus V lamp. Okay, and the switching action is occurred at the peak value of inductor current, and inductor current is varying fast. Okay, if the inductor current is varying something like this, switching action occurs here, here, something like that. Okay, so sampling effect is pronounced here. Okay, considerably pronounced here, and it affects dynamics of this converter. That is the basic reason where sampling effect is coming from, and why we are considering the sampling effect for the current mode control only, and not considering sampling effect in voltage mode control. Okay, suppose this is ideal case. V control is fixed. Okay, now assume there is some sinusoidal variation here in control voltage. So this is the ideal case, and the practical case may be something similar to this, something like this. Okay, so it also contains the sinusoidal oscillation, no magnitude oscillation, but this constant, this instant remain the same. Okay, so even though this control voltage has some oscillation and this point remain the same, that means this can be replaced with this line segment when their functionality are concerned. Okay, so this is fixed, but this is varying because this is derived from this fast varying inductor current waveforms. So there are significant sampling effect embedded into the system dynamics. Okay, so that is the reason why we are considering the sampling effect for the current mode control. Okay, we ignored this in classical analysis, and there are good reasons why we are okay without considering that. They will be explained later. Once you fully understand this sampling effect, then you can understand why we ignored the sampling effect in the classical analysis, and we are good in analysis and design and modeling. Okay, reason for that is explained later. Okay, and this is the waveforms we'll be using to address the sampling effect of current mode control. So this is the original circuit waveforms of current mode control. Okay, actually this is the modulator input waveforms. Again, V lamp is added to IL, and at this moment the switch is turned off and turned on again. Okay, and we modify this. So V lamp is here is plus, and this is minus. So you move this V lamp here and put minus sign here. Okay, then this is the same waveform, different waveforms, but it's the function is the same as the previous case. Okay, so now everything is very clear. So we are comparing with this and this IL. So IL hit this composite waveforms, then switch is turned off. Okay, so control action is determined by fast varying IL. IL is not continuous. Okay, and it's varying very fast. The slope can be changed immediately. So sampling here is entirely different. So sampling effect is embedded to the system dynamics because of this feature of the control mechanism. Okay. Assume this part is expanded. Assume somehow this part is expanded, zoomed out, then you have this. Okay? So this is the propagation of perturbed inductor current. This is original inductor current. So IL is this one, and increasing, switch is turned on again, and hit here, decreasing. This is the steady state, and it shows the periodic operation. Now assume somehow at this moment, disturbance is introduced here. So IL K hat is disturbance at case operational period. In the middle of the case operational period, this disturbance is introduced. Okay, and this is disturbed IL waveforms. This is the original undisturbed IL waveform, and we define this IL hat is error signal, error between here and here. Okay, and this is defined as this minus this, so it becomes positive. Okay, so actually our time. All right. Okay, so here there is no error because error is introduced here. Then there is error is like this. Okay, so this error initially introduced at this moment, which is this value minus this is this negative now. Okay, then it maintains up to this point. The error is increased here, but controller is not knowing that. Okay, because you are sampling only once in one switching period. So up this point, nothing happened. And when this perturbed inductor current hit this waveform, then this will start decreasing. Okay, so this is error. Okay, error is constant here, and this should be constant here. And at this point, error becomes 0. They meet each other, so error is 0. And during this period, you have error of this much. You have error of this much here, and you have error of this much at this moment. Okay, all right. So this is a true error signal. I labeled as unsampled error signal as this one. This is unsampled or actual, accurate or real error signal. Okay, but you are using the Mars PWM scheme, which is active only once in one switching period. So error is picked up here, but error remain the same. Nothing happens. And at this moment, error is sampled at this moment. Okay, error is sampled here. At that error is held constant onto the next operational period. Okay, that is very similar to sampling and zero order hold. Okay, maybe you may learn from the signal and systems or communication something, sample and hold circuit. It's not circuit. This function is the same as sample and holding this error signal. It only occurs once in every switching period, not continuously. Okay, that imprint the dynamic, that imprint the sampling effect, some sampled data feature in the system dynamics. Okay, so this is the unsampled error signal or true error signal, and this IL star T is sampled error signal. Okay, so IL star hat T represent the sampled and held constant held error signal. Okay, so we are using this, and because of this, the sampling feature is implanted to the system dynamics, and it shows up in the loop gain or some transfer function. This is the one good example. So I'm comparing here. This is the loop gain of boost converter. We'll be discussing this converter later, but just look at this. This solid line, this line, black line, this one is prediction of classical model, which does not consider the sampling effect. Then we have this. It maintains almost -1 slope here for the wide frequency range, and the phase is this one. Phase is decreasing linearly, and this one is the new model proposed by Ridley, including the sampling effect, and this is the simulation result with his model, and this thin line is computational method. measure the loop gain characteristic using the computational method. That is very similar to the experimental measurement. So we have some noise, okay, because of this high frequency there is a noise, and we have noise here, okay. But if you take a look at the average value of this or envelope of this and this prediction of this new model proposed by Ridley, if you compare this and this and this, okay, experimental measurement or computational method, this and this are very, very similar, okay. So this is the more accurate than the classical model. That is true, okay. And this one, the thin line is computational method, which is very similar, almost the same as the experimental measurement without some noise, reduce the noise, okay. And later on, you will see there is a peaking, and the peaking, value of the peaking is given by this 20 log QP, and QP is some strange function, not a function, some variable determined many parameters, like duty ratio and the slope of external lamp and the slope of on-time inductor, sensed on-time inductor current, and so on. Okay, so later on you will find this magnitude of peaking is expressed this simple equation. So when this QP is very small, the peaking is very small. Okay, if QP is very large, QP is much larger than unity. For example, 5, 7, or 10. Then this 20 log QP becomes very large. Then there is a peaking like this, and it can exceed this 0 dB line sometimes. Okay? Okay, phase. The classical model is here, but we know this sampling effect will introduce additional phase delay, or we know from the Middlebrooks modulator gain expression, there will be some additional phase unaccounted in the classical analysis. It is shown here. Okay, so think about this. This peaking. This is peaking. When peaking occurs, and the peaking occurs above this 0 dB line, then magnitude of this loop gain becomes larger than unity. That is the meaning of this 0 dB line. Okay. Think about the Nyquist plot for this loop gain, and this is the maybe prediction of the classical model. And classical model, this loop gain, polar plot of the loop gain is this one. Then this polar plot goes to the origin without touching this. Okay, but this you have this some portion extending out above the 0 dB line. That means this 0 is 1. 1 is a unit circle, so it goes in and it comes out this unit circle during this period, and the way it should go back to the origin, and the way it go back to the origin, during that process it encircles this critical point, then converter is what? Unstable. That is a prediction or theory of Nyquist analysis. I said the Nyquist analysis is most theoretically sound and very accurate criterion to determine the stability of any system. Okay, so this predict unstable oscillation at this frequency. Everything occurs at the Heptad switching frequency. This encirclement occurs at the Heptad switching frequency, and the peaking occurs at the Heptad switching frequency, and this phase delay of this is 90 degree about occurs at the Heptad switching frequency, and unstable growing oscillation will occur at the Heptad switching frequency. Okay, we had something very similar to this. That was the subharmonic oscillation. Okay, that occurred for the pure current mode control without external lamp. When duty ratio exceeds 0.5, the oscillation occurs. That oscillation, we call it subharmonic oscillation, but this oscillation is entirely different from this oscillation. That is the problem of current mode. Current loop itself, okay, without any feedback that occurs, okay. So that was the subharmonic oscillation, and oscillation frequency is the same but this behavior of oscillation is different. This is some arbitrary oscillation, but this was very systematic oscillation, something like this. Okay? So it's entirely different things. All right. Sampling effects are pronounced at high frequencies, namely in the neighborhood of half the switching frequency. That frequency is called Nyquist frequency. Right? So something is switching periodically, and half the switching frequency is called just Nyquist frequency. Okay? That's simple. So this is observable at this frequency only. So it affects only dynamics around here. Okay? So if this peaking is small, something like this, and there is a wide difference between this crossover frequency and this half-to switching frequency, where potential peaking will occur, you don't have to know this. Okay? So in the past, they are seeing this experimentally, but they forget about this. All right? And some people, they use some discrete time analysis technique, sample the data system, and they come up with some result which is totally useless. It's too complicated. Okay? Does not provide any information about this dynamics of the system, and absolutely there was no design information there. So they gave up long time ago, and they are using only classical analysis. And this guy, Ridley guy, and he investigate in the 1990, and he come up with a new model, which was new, and that time not new anymore. Okay, and I thought that is very important contribution. Okay, but maybe things change. Okay, all right. There is the introduction of the sampling effect. So sampling effect only occurs after half the switching frequency in the neighborhood of Nyquist frequency, and only in the loop gain, right? Because at the high frequencies, the closed loop transfer function is just copy of open loop transfer function. There is no sampling effect in open loop transfer function. Okay, so this occurs only in the loop gain and only in the neighborhood of this at high frequencies. But if it occurs, the system becomes unstable. It becomes useless. Okay, but it's very easy to avoid this disaster. All right. Okay, but we should model this. We should model this. Okay, so Raymond Ridley, that smart guy, proposed a method. Okay, the full details about this is written here. Chapter 8, section 8, 5, 7. Okay, everything is there. Okay, this is the summary. Very brief summary of that. So this sampling effect is coming from inductor current sampling. Okay, so control to inductor current is very important, because control voltage can change the inductor current, and inductor current is varying fast, and it changes the something, okay, switch drive signal, and that high frequency behavior is embedded in this transfer function. But this is the discrete time feature, sampling data feature, okay, and we use difference equation to analyze this, not differential equation, and we use G transformation, not S transformation, and he derived this, okay, transfer function from this control voltage to inductor current. Okay, this is the critical one, and somehow he derived this. This is the current sensing network gain. Alpha is this, given by this. This is the slope of sensed uptime current, inductor current, slope of compensation lamp, slope of on-time sensed inductor current. G is variable, complex variable in G domain. So he derived this, but this is the G domain. So we needed to convert that things to S domain, because the other part of converter every waveform varies slowly. Okay, so we have the S-domain model for the entire converter. Okay, only this part is we have G-domain model. So we convert this thing to S-domain expression. Okay, this is the procedure. You have some transfer function in G-domain, H-I-G. Then replace G, you have G in it. And you replace G with E2 STS. S is frequency variable, frequency domain variable, we are knowing. And you multiply this. This comes from the zero order hold characteristics. Okay. Then this becomes S domain expression. Is this one? This one. Okay. There is a long step in between. But I'm saying just the essence of this derivation. And you have this. You have S domain expression. But problem with this is called the transcendental function. Okay, it is not the linear function. Okay, so we need some approximation, and this can be approximated to this one. This is the conventional second order system. So we apply the Taylor series expression and one approximation technique called the Pardes approximation. Okay, you don't have to know every details about this, but through some several steps and some kind of approximation, he derived this. Okay, so this sampling effect is represented as the second order. This is 0. Okay, second order 0. It comes in the numerator. So he denoted as HES. But interesting thing here is this is S divided by omega n. Omega n is double pole frequency. Omega n is here, and omega n is given by Hampton switching frequency. Okay, so everything occurs at the Hampton switching frequency, and this is 0, and the QP, this value is negative. This is RHP 0. RHP 0. Okay, you know the RHP and LHP. So there is RHP 0. So actually this term is negative. Okay, this is the result of his model, and he has several other derivations. Okay, and so we derive this HES, and we derive something other which is also S domain function or constant, and we amalgamate. Amalgamate means we combine with this equivalent S domain model for the sampling effect into the existing. We already developed S domain model for slowly varying variables. So this S domain model was good when you are considering only slowly varying variables like out voltage, control voltage, and RAM signal. Okay. One exception is inductor current. Inductor current is fast varying variable. If the inductor current is involved in the control action, then you should go back to here. And that is represented here. Then you combine this and this. Okay, slowly varying variable means non-inductive current. Okay, all the current, voltage except the inductor current. All right. So this is the approach. Okay. Okay, this is one thing. Another one is when we are considering the classical analysis, we assume this IL remains the same. Okay, all the same. In the steady state, this IL remains the same. Okay, but somehow this IL is changed here. Okay, the slope has been changed. So initial IL is this one, and the perturbed IL slope has been changed. So this one. Okay, then with this regular unperturbed inductor current, this is a duty ratio, turned on, turned off. But with this, with the green one, this duty ratio is extended. Okay, this switch driver signal is QT, and this is Q prime T. They are different. So we have this much difference in duty ratio. That means the inductor current waveform has some influence. We didn't consider this before in classical analysis, but in the exact sense, there is a dependency between this inductor current perturbation and the duty ratio change. Okay, so we need to have some additional functional block. Okay, this is coming from the input voltage and output voltage altogether. Okay, for the buck converter case, the slope is on-time slope is this one. Okay, so this impact can come from this or come from this, and this case it come from this. Okay, so there is some functional relationship between input and output voltage of converter to the duty ratio variation. Okay, so the functional relationship between duty ratio and input or output voltage is represented by the feed forward gain. Okay, so this we have a feedback. This is feed forward. So they are different, but it has some profound difference between them. But I don't want to mention it here. So they are different. They are entirely different things. But they are gain, but feedback gain and the feed forward gain is very different in nature. Okay, but anyway, they are the number. Okay, so this is the complete S-domain small signal model. Okay, this is the conventional model. So when you are considering the voltage mode control, this is gone, this is gone, this is gone, this is gone. Okay, and this FMS was FM prime. Okay, in classical analysis, we use FM prime. Now we use FM star S. That means this is different. This modulator gain, including this sampling effect, is different from the modulator gain of classical modeling approach. Okay, and sometimes it is a function of frequency. Okay, previously it was constant. Okay, it can be constant some case, but it can be a function of S. All right. So for additional block, include this one. Okay, because of the current mode control, you include this, and because of the sampling effect, you added here, and this FM is changed when the sampling effect is constant. So we changed this, and there is some dependency between input voltage and output voltage to the duty ratio. So this is the control signal in here is affected by this one. So we have additional gain KF, KR, HES, and this was FM prime in classical analysis, but now this is FM star S. Okay. One thing, very important thing is this is very small. This KF, KR, they are not zero, but they are very small. Okay, that's very small, 0.1, something like that, or 0.01, something like that. This is very small. Okay, and there are two different approaches. Okay, let me explain this. The sampling effect can be embedded here. Sampling effect is frequency dependent phenomena. So it is a function of the S. Okay, if you take a look at this, HES is a function of S. Okay, so sometimes that the frequency dependence term comes here, and this one becomes constant, or this one becomes constant, and this one becomes frequency dependent term. The model we're going to use is one developed by the Lidley. In his model, this is constant and this is a frequency dependent term. There is another guy who derived a very similar model right after the Lidley proposed this. The guy name is Dongten, Chinese guy, and he has this modulator gain, frequency dependent modulator gain. And this one is constant. Okay, this one is 1. Okay, for his case. Okay, so sampling effect can be merged into this gain block, or here as the separate functional block, not both of them. Okay, only either of them, here or here. Okay, and this is called HES. If this is a constant, this becomes 1. Okay. For needless model, this is a very complicated one. We have seen this before in previous slide. Okay. And the KF and the KR are feed-forward gain from the input and out voltage, but they are very small. Okay. Suppose this. This is 1, this is 0, this is 0, and this is FM star. No, FM prime. There is what? There is classical analysis. Okay? So these are add-ons. This change here, and this one is add-ons. It's not entirely new. Okay? New analysis is using the frame of the classical analysis, and they added some blocks here as add-ons, okay, in the past, all right? But you realize this, for this case, this becomes the classical model, okay? If this is removed and this changed something, then that becomes what? Voltage mode control, okay? So basic analysis we learned from the voltage mode control extended to classical analysis, and all the knowledge you accumulate here will be used in the new analysis, including the sampling effect. Okay, so directly jumping into the sampling effect, that does not make any sense. Okay, so this is the gradual learning steps. Two prevalent S-domain model, two famous S-domain model in the past, not anymore. Okay, one guy is Didri. And Didri, he drive this, but this was constant, and these values are different, and his values and tense values are different, expression are different, and this is the constant, and HES includes the sampling effect, but this tense model, this is unity, directly connected, sampling effect is included here. Okay, so their model is different. Their modeling approaches are different. Their results are different. There are subtle changes between two models, and this model was developed. This guy was with Virginia Tech, where I graduated. Okay, so Virginia Tech people, they used this, and the guy, he's from the Caltech, where the Middlebrook is, okay, and the guys from the Caltech, they used this. They fought for 30 years. Maybe still they are fighting somewhere. Some dead people, they are fighting underground, like that, okay. I wrote one paper comparing this and this. I write some paper. His model was okay, but I claimed he made one mistake. If that mistake is fixed, that becomes his model. His model is very similar to the Freddy's old model. Okay, so I wrote the paper, and that paper was badly disputed. Okay, by Dr. Poporian. He was my colleague too. Okay. And miserably rejected for the publication. So still I'm keeping that paper. It's not published. Okay? But later on, I found the comparing this and trying to find which one is more accurate as meaningless, basically meaningless. Okay? That is my new result. Okay? If that paper was published, I'll be ashamed by myself. Okay, from the paper. Okay, all right. Okay, this is the Didris model. Okay, this is the result of the Didris model. All right. So this is the FM modulator gain of Didris model. Originally it was S, but I eliminate S because this is constant. All right. This is the Didris model, and this HES is represent the sampling effect of this inductor current feedback. This remains the same, but this HES is this one, and this is RHP00 because this quality factor is negative, and the the double pole frequency is this one. Okay, and the derivation of this is shown in the next 10 pages. Okay, so this morning, last night, I uploaded the derivation of this, but now we skip this. Okay, later on we will have a short lecture. Okay, so we skip. This is a derivation of this. Okay, so this is the detailed procedure of derivation of this. It's very long and tedious, not difficult. Okay, but it requires some the patience and some minor skill and something dishonest. Okay, during this process, we have this number is coming up. This is 4.9. But he approximates this to 4 without any reason. The reason is to make this nice expression. Okay? So this is acceptable, maybe, in engineering sense, but in exact sense, this approximation is doubtable. Okay? But somehow, with this kind of approximation, and he used this Pade approximation, and finally he come up with this. Okay? This can be considered acceptable in engineering sense. Okay, so we skip this, okay, because this is the final result, okay, of his model, right? Because if I go through this, it takes a long time and it distracts my attention and your attention. So we go through until the end of this story, and we come back to here and discuss this, okay? Just to justify what I'm showing here, okay? So this model, I already introduced this and this, okay? And this KF, KR is the feed forward gain from the out voltage and input voltage, okay? That is summarized here, okay? This one, okay? Same thing, okay? So I copied it twice because this will be used in the short lecture. This is the formal lecture, okay? So this and this is same as this. So this HES expression is common to all the PWM converters, and this expression is common to all the PWM converters, but this KF and the KR, this is the gain from the input voltage, gain from the out voltage, which is very small, much smaller than unity, is different from the buck converter, boost converter, and the buck boost converter. And this whole table is different when you go to the 10th model, Dong 10. His name, first name is Dong, last name is 10, Dong 10, Dong 10's model. Okay? They are still alive and they are very active and they are very rich and famous. Okay. Okay, so this is the end of 2 topics of the sampling effect, origin of sampling effect, and the modeling approach to sampling effect, and this model for sampling effect has been covered. Okay, and the derivation of this will come later on.